Hello everyone, I'd like to take the opportunity to thank you for coming here today. The subject of today's talk is unsupervised video-to-video translation with preservation of frame modification tendency. I'm the presenter Chao. My presentation is divided into 5 parts: introduction, related work, method, experiments, and conclusions. I'd like to begin by introduction. Nowadays, image translation is being widely used to synthesize vivid pictures into required styles. Likewise, we can also use a similar idea to translate the videos, which contains much more abundant spatial-temporal information compared to static image data. There are many approaches that try to synthesize videos into new styles using generative adversarial networks. RecycleGAN combines spatial temporal information along with adversarial losses for content translation and style preservation. Nonetheless, they tend to concentrate on maintaining the difference between adjacent frames, while ignoring the fact that the trend of frame modification in the generated video is also supposed to remain the same as in the original video. In other words, these methods are able to preserve some of the features in the source video, yet some information may be lost during the translation. For instance, in the video translation task, Stephen Colbert to John Oliver presented in RecycleGAN, the mouth motion of Colbert are captured, yet some face expressions in the source videos are lost after translation. To this end, we are motivated to make use of the consistent trend to synthesize videos that are able to preserve the content information in the source video. Based on this motivation, we propose an efficient method by removing an additional constraint, the tendency invariant loss, to ensure the consistency of the trend mentioned above. Let's take a look at the related work. First, we talk about image translation. There are many models referred to image translation, such as pix-to-pix, UNIT, CycleGAN, MUNIT, StarGAN. Pix-to-pix investigates conditional adversarial networks as a general-purpose solution to image-to-image translation problems. CycleGAN first introduces a cycle consistency loss, aiming to learn two mappings such that the translated source samples are inverses to the original samples. UNIT aims at learning a joint distribution of images in different domains by using images from the marginal distribution in individual domains. MUIT proposes the assumption that images of different domains can be mapped into separated latent space to synthesize images belonging to the target domain in a multimodal way. StarGAN is a novel and scalable approach that can perform image-to-image translation for multiple domains using only a single model. Now let's consider the videos, such as MocoGAN, RecycleGAN, and few-shot video-to-video synthesis. MocoGAN framework generates a video by mapping a sequence of random vectors to a sequence of video frames. RecycleGAN introduces a data-driven approach for unsupervised video retargeting that translates content from one domain to another while preserving the style native to a domain. Few-shot video-to-video synthesis achieved few-shot generation capacity via a weight generation module with an attention mechanism. As to the spatial temporal constraint, Tablet Proposal Networks is a framework video object detection, which consists of a tablet proposal network to generate spatial temporal proposals, and a long short-term memory network that incorporates temporal information from tablet proposals to improve the accuracy of object detection in videos. STMN proposes match trace module to align the spatial temporal memory from frame to frame. RPN represents videos as spatial temporal region graphs to capture the spatial temporal information whose nodes are connected by similarity relations and the spatial temporal relations between objects. I will introduce the method we proposed. The picture in the key idea of our method compared with recycle-gun. First, let's look at recycle-gun. It presents a way to deal with unpaired but ordered streams x sub 1, x sub 2, x sub t, and y sub 1, y sub 2, y sub t using spatial temporal constraint, which is the recycle laws introduced in their work. The whole cycle is across domain and time, and the L1 loss of the frame generated by capital G sub capital X and the real frame X sub t plus 1 is expected to be minimized. Then let's look at our method, which is based on recycle-gun. Not only considers the modification between adjacent frames, but also the modification tendency of the generated frames. The newly designed tendency invariant loss is minimized to ensure the modification trend of source frames is well preserved in the generated ones. The full loss structure of our work is as follows. Since we adopt the architecture of GAN, the vanilla adversarial loss is used as well, termed as L sub GAN in our work. And the cycle consistency loss L sub cycle in cycle GAN is adopted. Besides, the recurrent loss L sub recurrent and the recycle loss L sub cycle in recycle GAN are also leveraged. Meanwhile, we introduce a novel tendency invariant loss L sub invariant to imply the model and improve the whole translation. The parameters alpha, beta, gamma, and delta are used to balance the function. Then I will illustrate the novel tendency invariant loss in detail. As an improvement of recycle GAN, we dig further into the temporal information of the video. Apart from the above losses, we come up with a tendency invariant loss under the assumption that the frame modification trend ought to be maintained in the predict frames with the aim to preserve the content of source domain and improve the quality of the output. Capital P sub capital X of x sub t super t plus 1 denotes the prediction of frame x sub t plus 2 given x sub t and x sub t plus 1 as input. Capital P sub capital X of x sub t super t plus 1 minus capital P sub capital X of x sub t minus 1 super t denotes difference between the predict frames. This item denotes the modification between 3 frames, and it should be the same in the modification between 3 real frames. By calculating the difference of two L1 losses, we intend to obtain the tendency of the frame modification instead of merely the modification itself. Minimizing the tendency invariant loss means that we expect the frame modification tendency can be preserved in the predicted frames. I will introduce the experiments in our article. Although the cityscapes dataset is commonly used in other work, we consider it improper to be used in our experiments. For one thing, the labeled images in cityscapes are not in the form of continuous sequences. For another, RecycleGAN uses the Viper dataset to evaluate its effectiveness as well. Hence, we chose Viper dataset, face-to-face dataset, and flower-to-flower dataset that RecycleGAN provides to conduct our experiments and make the evaluations. To verify the effectiveness of our model, we compare it with models that focus on video translation with GANs. Since our model architecture is based on RecycleGAN and take unpaired video data as input, we chose CycleGAN and RecycleGAN as the baselines of our experiments. This figure shows an example of Trump to Obama. Both of the two methods are able to capture the stylistic face expressions of Trump. However, by observing the video, we should notice that the video generated by RecycleGAN is not stable compared to ours. Oliver to covert shown in figure. The detailed expressions are more correctly learned by our method than RecycleGAN. For example, in RecycleGAN, the flicker can be found in generated frames, while ours preserve the source content quite well. This figure shows the synthesized frames of our method on flower-to-flower dataset. Our method has a slight advantage over the baselines on FID scores, as shown in table. The user study also shown the advantages. This is the video translation results of RecycleGAN and our method on Viper dataset. As for the scores on the commonly used metrics for semantic segmentation, we can also tell that our method surpasses CycleGAN as well as RecycleGAN in pixel accuracy, mean pixel accuracy, and mean intersection over unit. We compare the FCN results of all the methods on different screens in the Viper dataset. We can conclude that videos generated by our method manifest the highest similarity to the input videos on 5 different screens. To evaluate the tendency deviation of our proposed method, we train our model and RecycleGAN on Obama to Trump dataset and record the tendency invariant loss. In the left figure, the loss trend during training is short, and we can see that the tendency invariant loss in ours is much lower than RecycleGAN's. The right figure shows the frame-by-frame comparison on one tested video sequence, where ours is also lower than RecycleGAN. These comparisons are meant to demonstrate that our proposed loss is able to help maintain the modification tendency between frames and achieve better smoothness. The last section is conclusion. Our method is proposed to tackle the issues of content preservation and video continuity during translation. Thus, we focus more on the modification trend between frames. For datasets that depict party and slight motions of subjects, the superiority of our spatial temporal constraint may not be apparent compared to recycle gun. This is the inherent limitation of our method, which we intend to work on in the future. In this paper, we propose an effective method to tackle the video synthesis using GANs based on the architecture of recycle gun. However, we are highly aware of the spatial temporal continuous information in the video, especially the invariant tendency of the modification between predict frames and the real ones. A normal tendency invariant loss is designed to constrain our model to synthesize videos that are more stable and preserve more content in the source video. I'm happy to answer your questions at the end of my presentation. Please feel free to interrupt if you have any questions.